Good morning, good afternoon, good evening, everybody. Today we're going to be learning about quantum theory, quantum mechanics, physics, chem, blackbody radiation, all of the above, everything that is good within the chemistry and physics world. So to begin with, we have a little bit of quantum chem / atomic history. So initially we have John Dalton, who basically said, here's an atom. Don't know what it looks like, but here it is. It can't be divided. There's a bunch of limitations to it. And 100 years later, he was upstaged by J.J. Thomson with the plum pudding model. So he basically said that it's a positively charged atom with a bunch of little negatively charged electrons scattered throughout. Now, this was a very, very controversial yet trailblazing idea at the time. But a couple years later, he was upstaged by Ernest Rutherford, who said that there was a positive nucleus and then you have the negative electrons orbiting around it. But 2 years after that, Niels Bohr came out with the planetary model that showed a more structured orbital pathway. But of course, after that, Schrödinger came out with the quantum model. And this quantum model basically states that electrons are moving about in a cloud. They don't have any set paths around the nucleus, and it is really impossible to know the exact location and the exact energy of the electron at the same time. So we have these clouds of probability. So Schrödinger basically said, all of you are wrong. We don't really know what's happening. So Schrödinger was a scientist who created the quantum mechanical model of the atom that happens to treat electrons as waves. His corresponding equation yields wave functions that are associated with binding energy, and in this equation, H means the Hamiltonian operator, E is equivalent to the binding energy of an electron, and psi represents the wave function. Now, when a wave function is squared, what does this represent? So this actually accounts for the probability of locating an electron within an atomic region. These regions, atomic orbitals, are where an electron is likely to be found 90% of the time. However, as Heisenberg's uncertainty principle states, we are unable to know both the position and the energy of an electron, so the more information that we have about an electron's position, the less we know about its energy. Now, what do cats have to do with this? So for some outside of the course content, we have cats and quantum theory. In quantum theory, at a single given time, quantum particles can exist in a superposition of states, collapsing down to a single state when interacting with other particles. And some scientists in the 1930s stated that particles will only collapse to a single state when evaluated by an observer. Now, Schrödinger thought this concept was strange and created his thought experiment to explain quantum physics. In this imaginary or thought experiment, a cat is placed in a box with a small portion of radioactive substance, and when this radioactive substance decays, it goes on to trigger a Geiger counter, causing a poison to be released, killing the cat. Sad, I know. But now, radioactive substance decay is controlled by the laws of quantum mechanics, meaning that the atom exists in a quantum state of going to decay and not going to decay. This shows that the collapse of wave functions are happening with or without a conscious observer, and this contradicts the Copenhagen interpretation of quantum mechanics that was theorized by Bohr, stating that observing a quantum system makes a wave function collapse into a single data point, such as trying to determine the position of an electron. So similar to the way that unless you open the box, you don't know if the cat is alive or dead, it treats an atom and the electron's positions in the same way. Now, to move on to quantum numbers are necessary to create a quantum description of molecular orbitals, and there are 4 numbers used to describe an electron in an atom. Using an analogy of a train, the principal quantum number, represented by n, determines which train a person sits on, or which shell the electron is in, describes the energy level, etc. Now, the azimuthal quantum number, represented by L, indicates which train car someone is in, or which subshell an electron is in, and provides the magnitude of the orbital angular momentum. Magnetic quantum number dictates which row or orbital an electron is in, and represents the projection of the orbital angular momentum along an axis. Now, spin quantum number talks about the seat, or the spin on an electron, giving the projection of the spin angular momentum. Now, these quantum numbers distinguish classical from quantum mechanics and play an imperative role in understanding how the classical laws of physics are broken down when observing certain phenomena. Now, what phenomena are we talking about? Drum roll, please. Blackbody radiation! So, blackbody radiation is a theoretical concept in quantum mechanics that states that a specific material or substance can completely absorb all frequencies of light. Now, the laws of thermodynamics state that an absorbed light must be re-emitted, and no material can actually be classified as a true blackbody, though carbon graphite represents a 96% efficiency, and the sun and stars are technically classified as blackbodies, though they are not true blackbodies. Now, the blackbody spectrum only depends on temperature and opposes classical theory in this way. And a theoretical true blackbody model absorbs all of the radiation given off and then re-emits the energy again, and the energy of these radiating waves at a certain frequency should, in theory, be proportionate to the quantity of modes at this frequency. We shouldn't really worry about this at this level, and there's an equation that corresponds with it, but that will be touched on later. So just a little explanation about blackbody radiation. If you think of Bruce Banner, he absorbs all of this gamma radiation and then possesses the ability to turn into the Hulk. So certain entities can absorb radiation and re-emit the energy in wavelengths, but the only known bodies to do that do not exist, just like, unfortunately, the Incredible Hulk. Sorry to break it to you. Back to the emission spectra. So how does this work? So in classical physics, classical mechanics, classical theory, they said, okay, so we know how this dispersion works over here on the right-hand side of the graph, but as it starts to go up into the visible light spectrum, which is where we can see, the light from the sun that's reflecting off of certain things and being absorbed, etc. We know what happens up to that point, but we don't know what happens after. So classical theory basically thought, you know what? I assume that this is going to go on infinitely, and that is called the ultraviolet catastrophe. So if classical theory was true, then every time that we would cook something in an oven, then we would be exposed to enormous amounts of UV radiation, which would not be good. Therefore, we had a nice little thing called quantum mechanics. Now, classical mechanics implies that we would expect most of the energy at a higher frequency, and this energy diverges with frequency. If we try and sum the energies at each frequency, we find that there is an infinite energy in the system, and this paradox is called the ultraviolet catastrophe, as touched on in the previous slide. Now, to go against the classical equation, Planck created an equation that quantized energy using E equals nhv, where n is an integer/quantum number, h is Planck's constant, and f is the specific frequency. Planck's theory was the first theory that truly opposed the classical theory and gave an explanation for the uninterpretable distribution of blackbody radiation spectra. According to Britannica, Planck's law describes the spectral density of electromagnetic radiation emitted by a black body in thermal equilibrium at a given temperature when there is no net flow of matter or energy between the body and its environment. Planck found that radiation does not escape the particular body and will oscillate inside of its cavity, kind of like shaking a bouncy ball inside of a box. The atomic oscillations, or the ball exchanging energy with the walls of the box, can only be present in discrete quanta. Thus, these oscillators have quantized energy. Since the ball only hits the side of the box at certain times, this represents the discrete quanta of energy that radiation will experience inside of this cavity. So now starting with practice problems. So we have a quantum oscillator, which, as I mentioned, Planck is associated with. So it's vibrating at a frequency of 5.0 times 10 to the 14 hertz. Calculate the spacing between its energy levels. Now, the energy states of a quantum oscillator are determined with the equation E equals nhf, and the energy difference must be found between these two adjacent quantum states. So if you want to try this question out, remember that h is representative of Planck's constant, which is 6.626 times 10 to the negative 34, just for reference. Okay, good. Now pause the video and figure that out, or you figured it out in like 10 seconds. Here's the solution. So we have E equals En plus 1 minus En. So that ends up simplifying to just HF because different things cancel out. Also, we add that plus 1 because it's at two adjacent energy levels. So then we plug in Planck's constant, we plug in the frequency, and then we find our amount of energy. Now, does classical mechanics explain this, or does it follow the rules of quantum mechanics? So convert the joules to electron volts using this constant. That was so quick. So the result is 2.8 electron volts, which is too large to be explained by classical theory, and quantum behavior must explain this answer. For the last practice problem, we are going to tackle wavelength frequency. So what is the wavelength frequency of a quantum of electromagnetic radiation if its energy is 2.0 kiloelectronvolts? So what you want to do first is you want to take Planck's relation, which is E equals hf, which is simplified into hc over lambda. So what you're going to do first is take Planck's constant, multiply that by the speed of light, and then you're going to have electron volts over joules, and then nanometers over meters. This is going to create a relationship between electron volts and nanometers, which can then be converted into your answer of this is your time to answer the question. That's right, 0.62 nanometers. You are all so very smart. And now you've determined the wavelength frequency of a quantum of electromagnetic radiation. I hope that you've learned something new in this tutorial, whether that be how quantum mechanics relates to a cat or the Incredible Hulk or a... Here are the lovely references. Hope that you have a wonderful day, and